Good morning, students. Welcome to today's class. Today we talk about lecture number 9, unit number 2. Okay. So we are going to discuss about the alternative pull-up networks and the switching threshold of CMOS inverter. So better I will write switching threshold. Switching threshold of CMOS inverter. Okay. So do one thing. Okay. Before going to this one, let us recapitulate what we have seen and where we have stopped, and let us continue with that. Okay. In the last class, quickly let us move that. In the last class, we have been discussing about VTC, voltage transfer characteristics of CMOS inverter. Okay. CMOS inverter. So there we have seen that the first case is that, of course, as we know that this is the CMOS inverter. PMOS must be a pull-up. NMOS must be pull-down. Pull-down is connected to ground. Pull-up is connected to VDD. Short circuit the two inputs, and the combined one is called VAN. The output is called Vout. Okay. So for this one, VN is changing from 0 to VDD. So 0 to VDD, we are changing. We are expecting that the output must fall from VDD to ground. This is what we are expecting. In this scenario, what we have done, first case that we considered that we are applying the input voltage between 0 to less than VTN. Okay. So less than that of the threshold voltage of NMOS transistor. Okay. So when the input is in between these two. Okay. So what we found that in this situation, we found that PMOS is on. Okay. PMOS is on and NMOS is off. Right. NMOS is off. So what is the meaning of this? NMOS is on, PMOS is off. On means here is linear. So why it is linear, that we have defined earlier. Off means it is in cutoff. Okay, it is in cutoff. So what we found from that one, we found that the Vout is actually exactly equal to VDD. Okay. So that is what we concluded in the last class. So that is what we have concluded in the last class. Agreed? So that characteristics that we have drawn, and the second characteristics is that case is that what happened if VAN is equal to greater than or equal, okay, greater than or equal to threshold voltage of an NMOS transistor. Threshold voltage of an NMOS transistor. Here also we found that a PMOS transistor remains on. Okay. And here NMOS will come into the picture. This becomes on. Okay. So it is cut off to on will be there. So as we mentioned earlier that it remains in the linear. Okay. And but this one, as soon as NMOS is on, it will be in the saturation region. Saturation. Why it is in the saturation region? Because the drain potential of the NMOS transistor is more than that of the gate potential of the NMOS transistor. So in that sense, the drain is more than that of the gate. Therefore, NMOS transistor will be in saturation region. This discussion we have already done in previous class. Okay. And we derived the characteristics is something like this. We have considered the VAN here. We have considered the Vout here. Okay. And we found that up to the threshold voltage of an NMOS transistor, up to the threshold voltage of VTN, when Vn is equal to 0 to VTN, this is what holds good. This is a VDD value that we got. Okay. When it is beyond our VTN, exactly at VTN or beyond VTN, what is happening here? NMOS transistor is on. Or I can simply write this approach. Instead of saying that, of course, it will be greater than or equal, but when exactly at VTN, this is what happening. There we found that there is a parabolic nature that is observed here. Okay. So this is the nature that we observe. Why it is so? This is kind of behavior is observing. We are able to observe. The reason is that NMOS and PMOS both are on. Therefore, the current flow, PMOS current linear current equation, NMOS current saturation current equation must be equal. And if you take the relationship between here, actually I can say that since it is in a linear relationship, IDSN is equal to IDSP outundi. Okay, kada? So both currents are equal. So that is what we observe. In that situation, because of this relationship, it will be some parabolic nature in this way. Okay. So this is observed in this fashion, right? Now, fine. What happened if Vn is equal to more than that of that value? So that means we want to say that how long the PMOS transistor becomes on. How long the PMOS becomes in linear region. That's what we need to know. How long the PMOS transistor is in linear. Somehow it must come out of the linear to some other region. Okay. Okay. So when it will come out of that one? For that one, we derived that one equation. So what is the equation that we have derived in the last class? Is the equation that we have derived in the last class. Okay. Eighth lecture. This is the eighth lecture. In this one, what we derived. So we have derived in this one. Okay. So when V out is equal to Vn minus of magnitude of VTP. So this is the line where exactly we found that the transistor will come out of the linear region. So the same thing that I'm going to write here, V out is equal to Vn minus of VTP. So I'm going to write here is this is, for example, not this much. So this is a line that supports that the V out is equal to Vn minus of VTP. So at this point, I can say that at this point, the PMOS transistor will come out from linear to another region. Okay. So actually, as I mentioned in the previous, it is entered into the saturation region. It will enter into the saturation region. Okay. So the third case is that the third case. Okay. Okay, so we will define what is the values of this one. For the time being, just you understand that in the third case, what we observe that when the V out is equal to VAN minus of V out, we'll make sure that PMOS will enter into saturation. Okay, that is what we have derived in the last class also. Okay, so therefore what we observe now in this case now, NMOS is on, of course, it is in saturation. PMOS is also on, that is also enter into saturation region. This also enter into saturation region. What do you mean by this one? That means IDSP is equal to IDSN. What kind of relationship here is the saturation relationship? This is also a saturation relationship. Okay, therefore both are saturation relationship. Therefore it is just like a straight line equation, equation that we'll get it here. So that's the reason why I will write here is that, so this is the transient, this is the region straight line equation where we find that NMOS is in saturation on and PMOS is also in saturation. You can equate the current equation, beta by 2 into VCS minus of VTH whole square is equal to beta by 2 into VCS minus of VTH whole square. Left hand side, right hand side, square will get cancelled. Okay, it is just like a straight line equation. Therefore, there's a reason why it is decreasing fashion straight line. Okay. Now, so as we know that the NMOS, PMOS is just now entered into the saturation region, fine. But NMOS is available for the two regions. Okay, here also NMOS is in saturation only. Here also it is entered into the saturation, available in the saturation. So that means that NMOS will enter into another region. Okay, again it is entered into another region. At what input voltage the NMOS will enter into another region? That's what we have to find. Okay, so therefore the fourth case, what we say that the fourth case is, here I can write both transistors are in saturation. Now the third kind we want to consider that NMOS region of operation changes. So when it will changes its operation, okay, we know that the equation VDS value we have to calculate. Okay, we have to calculate VCS value, VDS value, and we have to calculate the VCS value of this transistor. Okay, so edge of the saturation is more than sufficient to find out this one. Okay, so what is the value of the VDS? VD minus of VS is available here. VC minus of VS is available here, and VTN. What is the VD of this transistor? So VD of this transistor is actually connected to Vout, right? Therefore, that is called Vout. What is the VS now? Ground. It is connected to ground. What is the VC? It is connected to input. What is the value of the VS? That value is 0 minus of VTN. So therefore, Vout is equal to VAN minus of VTN. Okay. So the output voltage we are getting less than that of the threshold voltage. So let us consider the typical values, for example. So typical values. So what are the typical values? VTN is equal to positive 0.4 volts. Okay, but in case of PMOS transistor, it is a negative value. Okay, so if you consider that one for VN is equal to changing from 0 to some value, for example, 0 to 5 volts we consider, for example, what will happen? What is the line that we get here now? Vout is equal to pi minus of 0.4, pi minus of 0, sorry. For example, I'm sorry, we have 0 in start of another, yeah. That is starting from 0, 0 minus 0.4, 0 minus 0.4, 0 minus, sorry, 1 minus 0.4, 2 minus 0.4, something like this, up to the 5 volts that we need to consider. That means that it is minus 0.4, this is 0.6, it is 2.6, something like this it is going. That means this is the line it is saying that. So you can observe here the line. So what is the line? It is saying that it is after the threshold voltage it is starting. Okay, so I can simply write that after the threshold voltage. Excuse me. This is the line. This is the line where what is the line? It is saying that this line is actually meant for V out is equal to VAN minus of VTN. This is. So this line, whenever the characteristic curve touches this line makes sure that NMOS transistor will enter into the linear region. NMOS transistor will enter into the linear region. Okay, so that's what we observe. So therefore, this is the point that we need to observe. So this is the point that we need to observe here. Right? So therefore here, for sake of completeness, I'll write the PMOS is in linear. Here, NMOS is off, completely off. PMOS is in linear. Okay, now fine. Now, so therefore, the NMOS transistor is come out of the saturation region to the linear region. Okay, that means some point is there. Here is a maximum value is equal to VDD. Okay, when the PMOS transistor will come out from saturation to the cutoff region. Okay, ultimately what we observe that from the first point of view, as we give the 0 volt, only we observe logic 0, the PMOS is only on, NMOS is off, only on, but NMOS is off, right? That's what we observe. At maximum voltage, that means at exact at logic 1 value, PMOS is off. Okay, PMOS is off. That's what we observed, and NMOS is on, right? That means we know that. That means we know that at the maximum voltage, input voltage, PMOS is obviously off. At maximum input voltage, PMOS is completely off. That means whatever the region previously it has got, when it reaches to the maximum input voltage, that the PMOS transistor is all, PMOS transistor will be off. Right? That means we are observing that a PMOS transistor in the saturation region. So when it is approaching to the VDD, the PMOS transistor should be off. Okay. So at what input voltage? At what input voltage it is coming from this region to the cutoff region? At what input voltage the PMOS transistor is starting from saturation region to the cutoff region? Okay, that's what we need to write. Okay, so next is the region where PMOS enter into cutoff. So cutoff look vellali ante reason cutoff look vellali ante meaning ante emovutundi manaki we need to calculate. So VGS, okay, so cutoff region loki vellali ante off avvalante meaning enti manaki VGS that we have to calculate of the PMOS transistor greater than or less than. Anyone? PMOS transistor off avvali ani ante VGS ki VTH ki what is the relationship? Anyone from the class? For NMOS, yeah, it is no, for the PMOS for NMOS transistor off avvalante less than VTH unte, VGS value less than VTH unte, it will be off. Whereas in case of PMOS transistor, it should be greater than that of the threshold voltage, right? It is greater than that of the threshold.
Just a modulus add chesi saripothundi annaru.
Yes, that approach is also there. Yeah, that approach, according to that approach we can do it, but I'm not doing according to that approach. I'm doing the physical orientation. Okay, so I'm not using any kind of modulus values. Whatever the physical values are there, negative values are there, I'm playing with that one only. That's the reason. Okay.
Yes, sir.
Yeah. So in the previous class, we said that VCS of NMOS transistor is less than VTN, then the transistor is off. Okay. When VCSN is greater than VTN, then we can say that greater than or equal, it is in on. But exactly opposite. When VCS value is greater than VTN, it is off. When VCS of PMOS transistor, I'm talking about the PMOS. PMOS, it is also PMOS. Is less than VTP, then it is in on. That's what we found that. Okay. Therefore, this value should be greater than, or I can say that equal VTP, then it should be off transistor. So this is a off condition for the PMOS transistor. So I can consider that the VCS value. Okay. What is the VCS value now here now? It is nothing but VC minus of VS greater than or equal VTP. So what is the VC here? Simply VN. What is the VS? It is connected to VDD greater than or equal to VTP. Okay. Now the input voltage at which greater than or equal to VDD plus VTP. VDD plus VTP. So this is the voltage. This is the voltage at which the transistor PMOS transistor will enter into the cutoff region. Okay. So can you take the typical values of this one? What exactly meaning of this one? అంటే VDDకి less than VTP ఉండాలి. So VTP value negative actually. VTP value is a negative value. అంటే 5 volts. So for example, input voltage 5 volts. What is the value of this VTP? Plus minus 0.4. Okay, na? That means 5 minus 0.4. That is 4.6. So that means at the 4.6 voltage. అంటే ఇది VDD అనుకోండి. Less than threshold voltage. For example, up to this point. At this point. Agreed? So what is this point we normally call it as? What is the point that we normally call it as this one? VDD plus VTP. VDD plus VTP. At this point, I can say that I'm sure that I can draw this value. Okay, so at this point, that means up to this point onwards, what I can say that NMOS is on, but PMOS is off. Agreed? So from this point onwards, VDD plus VTP onwards, this is happening. Now what happened between these 2 points then? So ikkadi nunchi ikkadiki ela untundi mari? The common sense we can say that it's very simple to identify. So before that one, NMOS is on, PMOS is also on. So by the way, what is the condition of the saturation? What is the NMOS transistor condition? Is it in saturation or linear region? As we mentioned that it is in the linear region. For okay, better I'll write it for NMOS. NMOS will enter into the saturation region demarcation line. It is PMOS transistor will enter into the saturation demarcation line. Okay. So therefore, NMOS is in linear region, PMOS is in saturation region. So what is the condition here now? Please remember carefully. So here NMOS is on only, but it is in linear. And here is the PMOS is in on only, but it is in saturation. So therefore, this one and this one, and for example, let's region 1, 2, 3, 4, and this is the 5 regions are there, for example. So therefore, region number 2 and region number 4 are similar to each other, but the PMOS and NMOS operations are different. Region of operations are different. But anyway, it can be written in this way. So this is also a parabolic in nature, and we'll enter into this one. Right? Is it clear to all of you how we have derived all this? What are the different regions that is available in the CMOS inverter region of operations, especially in the inverter? Right? So therefore, this is what we can say that the VI characteristics of, voltage transfer characteristics of CMOS inverter. Therefore, let us conclude very quickly for this one, in this one, conclusion. What is the conclusion for the VI transfer characteristics? For example, you consider in this way, is the VN, it is called Vout, up to the threshold voltage of an NMOS transistor. So this is actually VTN. Both the transistors are on. So the one transistor is on, another transistor is off. Next, it will go down to the saturation, and it will enter into the linear and this one, and it will go to the. So this is the maximum value of the VN, maximum value of the VDD. This point, okay. So I'll write here is this point. This point is important. This point is important. This point is important, and this point is important. Okay. Right. So let us write here is NMOS is off. For simplicity, I'm writing N and P. PMOS is on, the two in linear. Here NMOS is on, it is in saturation, and PMOS is also on, it is in linear. So okay, here NMOS is on and PMOS is also on, but both are in saturation. So at this particular region, both the transistors are acting as a current sources. So NMOS is on, but it is in linear. PMOS is in on, but it is in saturation. So here NMOS is completely on, and but you can say that it is in saturation, but the PMOS is in off, but it is in cutoff. Okay, so that's what we have to remember. So therefore, from this voltage transfer characteristic, we can identify that whenever we are applying the logic low value, so logic low value, we got high value. Whenever you apply the logic high value, we got 0. Okay, therefore, we can simply write whenever the VN is equal to 0, Vout is equal to absolutely equal to VDD. There is no doubt at all. There is no doubt at all. Okay, when VN is equal to VDD, for example, if high voltage, if you apply our logic value, logic high value apply, Vout is equal to absolutely equal to 0. So therefore, this is what the biggest advantage of using the CMOS technology. CMOS technology in the sense, how many number of NMOS transistors are there, those many number of PMOS transistors you should use at the pull-up network. Okay, so you find that the different inverters, okay, resistive pull-up inverter, depletion pull-up inverter, enhancement pull-up inverter. So all these three categories does not produce this kind of approach, because somewhere else, somewhere we found some kind of problem. But in case of CMOS, the VN and Vout, the output voltage values are absolutely the supply voltages. Okay. Now, at this point, we want to write one important thing. So what is the current characteristics of this device? So better I want to write it here itself. What is the current, when the input voltage is increases, so what is the current characteristics? Okay, I will write it separately. So for example, this is what the VN. So within the Vout curve only, I want to write it here. So as we know that this is what actually happening. Okay, so at this point of time, what is the current characteristics that we observed at these four regions? Observed here the current is equal to 0 because one transistor is on, another transistor is off. Since a parallel connection, there is no current flowing. But here the current will flow, right? But here the current will flow in this particular region because both NMOS and PMOS transistors becomes on. One is in linear, one is in saturation. That means current is slowly increasing. So when it reaches to the maximum value, at both are at saturation region. Both are at saturation region. Okay, maximum current will be observed at this point. So whenever it reaches to this, from this point onwards, it starts decreasing and go back to the value. So therefore, this is called actually the current available in CMOS inverter. Current characteristics in CMOS inverter. So when the maximum current will flow, when both the transistors are on, but we don't want to use this kind of a scenario in our digital applications. We want to operate it at this either high value voltages and low voltages. But actually, we found that we thought that at static voltages, for example, when Vn is equal to 0, keep for a long time, both the transistors are not on, only one transistor is on. Okay, and Vn is equal to VDD, for example, only one transistor is on, another transistor is not on. So therefore, under steady state condition, there is no short circuit power consumption existed. So there is under steady state condition means up to this point and up to this point. So there is no static power consumption existed there. But the point at which both the transistors are on will give you the, so these are the place where exactly both the transistors are on. It consumes some amount of the power because there is a short circuit power is existed between the VDD to ground. Okay, there is a short circuit is existed between the VDD to ground. So because of that one, power consumption is there, but that power consumption is very small. That power consumption is very small. So the power consumption, static power consumption is static power consumption. Static power consumption is small, very small when compared to the other things, because this region is very small. So this region is very small. That's the reason why there is a possibility of both the transistors on will be very less. Okay, therefore the CMOS is very dominating when compared to the other technologies is because of a very small range of region for both the transistors is on. Okay, what is the ideal characteristics of an inverter? So మనం మామూలుగా అయితే ideal characteristics ఎలా ఉండాలి మనకి? Ideal characteristics, let us write an ideal characteristics. So ideal characteristics is something like this. So it should be high, low, and this is 0. So this is what an ideal characteristics. So we start here is 0, it is actually VDD. So therefore, this entire region is meant for, logic 0. This entire region is meant for logic high. This entire region is meant for logic high. So this is meant for logic low. But actually it is deviated from that one. How it is deviated? It is available up to this point and reaches to this point and something like this. Something like this. So it is actually, it is not identical to that of ideal characteristics. So there is some deviations are there because of its that we cannot find idealities in the MOS transistors. Therefore, it will be there in that way. Now, it's very important to note one important point. It's very important to understand the switching threshold of a transistor, of inverter. Switching threshold of inverter. It's very important one. So what do you mean by a switching threshold of an inverter? We want to, as I mentioned, that the power consumption is existed in the CMOS device only when both the transistors are on, and the point at which the maximum current will flow, the point at which the input voltage at which the maximum current will flow will be called as switching threshold of an inverter. The maximum current at which at what input voltage we observe the maximum current is called the switching threshold. at that particular voltage, Vn is equal to Vout. Then, at that particular voltage, Vn is equal to Vout. And as I mentioned that in this way, so high, something like this it is going. So this is the point where actually some saturation region to saturation region, maximum current will flow. Am I right? So maximum current will flow from this point. Okay. So that means both the transistors are on at that point of time. The input voltage is equal to the output voltage. That's what we observe. So at what input voltage, this is what observed. At what input voltage, input is equal to output is observed. Okay. So in order to find out that, so this voltage, so this particular voltage we can call it as switching threshold, or trip point also we can call it as. What we can call it as trip point. Is also called as trip point. So the trip point is, or the trip voltage is nothing but the voltage at which both the input and output are equal. Or I can say that the maximum current will flow in the CMOS inverter. Okay, that observation is necessary. Of course, it is better in terms of other devices, but it's very important. So it's very easy to find out VST. How do we calculate this one? So as I mentioned that Vn is equal to Vt is observed at both the transistors are on, that too in saturation. Therefore, I can write IDSP is equal to IDSN. There. So I should take this the saturation current equation, and here also I need to take the saturation current equation. So these both must be on, the both must be evaluated and take the common point. Okay, so we have to calculate all these things. Shall we do that one quickly? Okay, so here, what is the current equation for the VCSP? What is the current equation? Beta P divided by 2 into VCSP minus of VTP whole square is equal to beta n divided by 2 into VCSN minus of VTN whole square. Agreed? So this is the point where I want to calculate my switching threshold, because the maximum current will flow here itself. That is the point where I can observe that Vn is equal to Vout. Okay. So how do we measure this one then? Beta P22 will get cancelled. I can say that Vc of PMOS transistor, Vs of PMOS transistor minus of VTP whole square is equal to beta n into Vc of NMOS transistor, Vs of NMOS transistor, Vtn of NMOS transistor. Okay. So I can write what is the VCP here now? VCP stands for VAN, right? Gate voltage of the PMOS transistor is VN only, VAN only. That VN is actually Vout. That Vout is actually V switching threshold, right? So this I can write V switching threshold. I can write it, right? Minus of what is the VSP? VS and it is connected to power supply VDD. Minus of VTP whole square. Therefore, this is beta n divided by beta p. I can write it here for sake of simplicity. And what is the VCN? It is input voltage that is equal to Vout, that is equal to VST. Therefore, VST I can write it minus of VSN. VSN is actually 0, right? It is connected to ground. Okay, so it is connected to ground minus VTN whole square. So how do we calculate? Now we have to take the VST switching threshold voltage. I need to calculate. So what to do? What should I do then? Square square 2 times both sides తీసేయాలంటే ఏం చేయాలి మనం? ఇలా స్క్వేర్ రూట్ ఇక్కడ అప్లై చేస్తే సరిపోతుందిగా. బీటా n divided by beta p. Okay, into VST minus of VTN something like this. Okay, square both sides, square this element, square root kawali. Therefore now we have to calculate VST. So what is the VST we need to calculate? For the sake of reduce the time taken, so I'm going to use snipper tool. Listen. Snipping tool, open. So this is what we will get there. Copy and then paste here. So this is the what the input. This is what we can observe. Okay. So this value is VST, switching threshold or the input voltage. Okay. So input voltage or switching threshold, both are the same. It becomes VDD plus VTP plus VTN, beta n divided by beta P whole square into this one. So this is what we can derive from that one. It's very easy. Nothing else in it. Okay. So from this point of from this equation, we can write some typical values. Okay, assume that what exactly value the VST in a transfer characteristics we will find out. Assume that VTP is equal to VTN. VTP is equal to VTN, and beta n is equal to beta P. Beta n is equal to beta P. That is only the choice is there. Under this situation, what we observe that VST is now VDD. So both will get cancelled. So what is happening here? Beta n is equal to beta P means this will be get cancelled. So this, both are equal means it's only 1 4 1 by 2 is nothing else, nothing is there. So these two will get cancelled. So this becomes 1, this becomes 1. So therefore what is happening here? P divided by 2 will be observed. So that means the input voltage at which, so if the input voltage is VDD divided by 2, whatever the maximum power supply is there, exactly half of the maximum power supply, you can find that maximum amount of the current will flow, at which the input voltage is equal to the output voltage. Okay, so that means that, so we observe that whenever we are writing this equation, this transfer characteristics, okay, exactly at the middle point, VDD divided by 2, both the transistors on, maximum current will flow. So therefore, this is called a switching threshold of a CMOS inverter. Switching threshold. So this is called switching threshold. So what is the condition where both the transistor becomes on, and that too Vn is equal to Vout? That is called switching threshold. So what is the switching threshold of a CMOS inverter? Exactly VDD by 2. Okay. So what is the assumption that we have taken? Just I will take another 2 to 3 minutes and I will complete it. What are the assumptions that we have taken? Beta n is equal to beta P. So apart from the threshold voltages, I have considered beta n is equal to beta P. Okay, that is under this assumption I got that trip voltage is VDD by 2. Okay, so what is the meaning of this statement? So as we know that this is actually mu n into W n divided by ln. That is what the meaning of beta. What about this PMOS transistor? This is mu p into WP divided by LP. Okay, so generally the length of the NMOS and length of the PMOS both are equal. Therefore, I can cancel together. Okay, that means that what can I do here now? Mu n into Wn is equal to mu p into Wp. Everybody knows that. So the mobility of the electron is equal to 2.5 times the mobility of holes. That means mobility of the electrons are more than that of the mobility of the holes, because the electrons are freely moved, but the holes are moving in the covalent bonds. Within the covalent bonds, it can move. It is moving in the covalent bonds. That's the reason why mobility of the electrons or holes are less. So mu n is actually what is the value that I can write? 2.5 times of mu p into Wn is equal to mu p into Wp. So mu n will get cancelled. Therefore, 2.5 times of Wn is equal to Wp. So what this equation says that, if you want to find out the V switching threshold voltage is equal to VDD by 2, you have to maintain that width of the PMOS transistor is equal to 2.5 times of width of NMOS transistor. We have to maintain this relationship, then only it is possible. Why we need to do this one? So because if the trip point is middle of that one, for example, then there is a equal margins for the logic low value as well as for the logic high values. Equal margins and a symmetrical operation. There is a symmetrical operation that's observed. That exactly we do by 2. Symmetrical operation. That means NMOS, that means inverter and the logic 0 ki ఎంత అవైలబిలిటీ ఇస్తుందో లాజిక్ హై కూడా అంతే అవైలబిలిటీ ఇవ్వాలి అని అంటే we have to maintain WP is equal to 2.5 times of WN. Okay, so that means that whatever the PMOS transistor you considered here, okay, for example ఇక్కడ 1 యూనిట్ తీసుకున్నాను అనుకోండి, ఇక్కడ ఎంత తీసుకోవాలి WN దీనికి 2.5 times తీసుకోవాలి. For example 20 ఇక్కడ తీసుకున్నాను అనుకోండి, so 2.5 times of 20. That is the size ratio that we have to maintain. If you're not maintain the size ratio, something like that, and the symmetrical operation cannot be possible. So let us see another case. Okay, what if, for example, as I mentioned that case number 1, beta n is greater than beta p. Etla chesanu for example, atla తీసుకోలేదు నేను, beta n ఎక్కువ తీసుకున్నాను, అప్పుడు ఏమవుతుంది? What we observe, and Wn is equal to 2.5 times of Wn is greater than Wp. Wow, I think in order to say this one, that means that width of the NMOS transistor is higher than that of the width of the PMOS transistor. That's what the meaning. So what is the simple meaning of this statement? Width of NMOS, is more than PMOS. Under the situation, characteristics will change something like this. So therefore the characteristics will move, the trip point will move towards the ground side. So the trip point becomes now this value. It's not VDD by 2. Okay, please observe, it's not VDD by 2. It is moved towards the ground side. And please observe that. So what is the meaning of this statement now? The meaning of the statement is only the availability is this point for the logic low value, but this much value is meant for, this is for the long duration is there for the VDD. That's what we observe. So because the trip point is moving at this point, right? Trip point is available here. Trip point is moving towards the ground side. Okay, so therefore, if you consider another case, for example, case number B, if the beta n is less than beta p, okay, and WP is more on the equal ga more on the, so appude evavutundi manaki, which means that width of PMOS is more than NMOS. In this situation, what will happen? See, observe. So the trip point will move towards the VDD side. Trip point will move towards the VDD side. Trip point is available here. Okay, so that means that we say that there is a small duration is available for this one. There is a small duration is available at this point, but there is a long duration is available for this one. So therefore, there is no symmetrical operation if the Wn and Wp are greater than or less than, but there is a symmetrical operation can be observed for the beta n is equal to beta p ratio. Okay, so therefore we have to maintain like that only. So this is the best solution for both NMOS and PMOS operated reasonably in order to find the rise time and fall time characteristics. Okay, so but this is actually beta n is less than beta p. Here is beta n is greater than beta p. So here is actually beta n is equal to beta p. So if the beta n is equal to beta p is then width of the NMOS transistor is 2.5 times of the this one. So ekrana disturbance వచ్చింది అనుకోండి, then it is not possible to find out that one. So for the symmetrical operation, this is the best choice. Okay, please remember this one. So with this, we have completed the today's class. We will see the remaining things in the next class. So the tomorrow's class is the last class for the unit number 2. Okay, thank you. Thank you very much for patiently listening. Stop here.